Hi, this is a supplementary math lesson for advanced math, lesson number 60, factoring trigonomic equations. We're going to use our tools of factoring to come up with solutions to trigonomic equations, just like we did in algebraic expressions. Okay, so for instance, in this algebraic expression, and I am using the examples on page 392 and 393 of your textbooks. If you want to pause the video and crack your books open to those pages now, go ahead and pause the video. I am starting with example 60.1, excuse me, at the bottom of page 392. We look at this trigonomic equation. We can see we have a tangent function squared, okay, minus a 1. Okay, we can recognize this as a difference of two squares. This first term represents the tangent of theta times the tangent of theta. It's a little more difficult to realize because, remember, when we express a square of a trigonomic function, we put that squared symbol between the trig function and the theta. Okay, it's just the convention we use. Okay, but it's no different than an x squared minus 1 we recognize as a difference of two squares. Okay, how do we factor a difference of two squares? We factor them into their conjugate pairs. Okay, what is the square root of the first term? It's the tangent of theta. What's the square root of the second term? It is 1. Okay, the second term in those pairs, one of them gets a positive and one gets a negative. That's the conjugate pair. Okay, that's what difference of two squares factors into. To get the solutions, we set those factors equal to 0. Okay, so we set tangent of theta plus 1 equal to 0. That means tangent of theta equals minus 1 is a possible solution. Okay, we set the tangent of theta minus 1 equal to 0. That means the tangent of theta can be a plus 1 as a possible solution. Okay, so when are the tangents in our reference triangles, when we do our reference circle, equal to 0? When is the opposite leg over the adjacent leg equal to 1? Okay, it's when those legs are equal in length, when there's a 45, 45, 90 triangle. Okay, on our reference circle, where does that happen? It happens everywhere a 45-degree angle is made back to the x-axis. Okay, so our first 45-degree angle would be up here. Okay, back to, that's our first reference triangle. The tangent at that point is plus 1. Okay, that represents 45 degrees. Okay, we can get another 45-degree triangle over here, back to the x-axis. The tangent is minus 1 there. Okay, that angle is 135 degrees from our starting point. We can get another 45-degree angle. In this case, the angle is this one back to the x-axis. Okay, we have a negative cosine, a negative sine on that triangle. It equates to a positive tangent, a positive 1 for tangent. Okay, that angle ends up being all the way around 225 degrees. Okay, and we get one last 45-degree triangle here back to our x-axis, the reference triangle being the reference angle being there. That returns a tangent value of minus 1. Okay, and that is an angle of 315 degrees. Okay, if we start at our x-axis and go all the way around to measure it. So those are our 4 possible solutions for theta. Okay, can be 45, 135, 225, and 315 for this trigonomic function. Okay. Going to example 60.2 in the book. Okay, we have this trigonomic expression. And again, we can factor it the same as the algebraic expression. We're going to factor out the sine of theta. Now remember, we had that discussion, and I have trouble pronouncing this word, the inviolable argument in trig functions. We cannot separate the argument of the trig function from the trig function itself. Well, we can't factor that out of the trig function because we substantially change the equation. We do that. So the argument, the part of theta or expression of theta in parentheses that follows the trig function, we must keep that attached to the trig function in our problems. They're joined at the hip. If we break them apart, okay, we're substantially changing the math of the equation. Okay, but here we're keeping them together, the sine and the theta. We're just going to factor out a sine here, and here it's going to be minus 1 equals 0. Okay, now in this case, we set the sine, these are our two factors. We set the sine of theta equal to 0. We set the sine of theta minus 1 equal to 0, and go through the same drill coming up with possible solutions. Okay, example 60.3, we see here, well, before we start factoring, remember, we have to set the expression equal to 0. So we're going to change that to the cosine squared of theta minus 1 equals 0. Okay, now we notice we have the same situation as we did here. We have a difference of 2 squares. Okay, we factored this expression into the conjugate pair using the cosine function. The cosine of theta plus 1, the cosine of theta minus 1 is our factors for that difference of 2 squares. We set those equal to 0 and come up with possible solutions for theta, and all of these are in the realm of 0 to 360 degrees. Okay, so it's a rather easy transition between factoring these trig functions. The same thing we've been doing with algebraic function. Now, I'm going to combine lesson 60.B with this one. If you turn to page 394, turn the page over. So they're saying there is a particular thing, a particular procedure we have to be aware of when factoring trig functions, okay? And they give an example. The 2 sine of x times the cosine of x equals the sine of x. Okay, so they say, well, we can try doing this. We have a sine of x on either side. Okay, if we divide both sides by the sine of x, okay, we would get a cancellation. We would get the 2 cosine of x equals 1. Okay, we would get the cosine of x equals, we would divide out the 2 equals 1/2. Okay, so we would find on our reference circle where does the cosine of x equal a positive 1/2. Okay, in their example, that occurs when x is equal to 60 or 300 degrees. Okay, but they said if we factor that problem in a different way, okay, instead of dividing by that sine of x, okay, in fact, if we took the sine of x over onto the other side, in other words, we made that expression the 2 sine of x cosine of x minus the sine of x equals 0, okay, and then we factor out a sine of x, we get a 2 cosine of x minus 1 equals 0. okay, then these would be our two factors. We would then set those equal to 0, sine of x equals 0, the 2 cosine of x minus 1 equals 0. Okay, we notice this 2 cosine of x would reduce to, if we add 1 here, add 1 to the other, send that 1 over to the other side, and then divide out the 2, okay, we have that same expression here that we did when we divided out the sine of x. But when we divided out the sine of x, what we don't have as a possible solution is this factor right here. And they're saying, in that case, that factor gives us 2 additional solutions, okay, where x could equal, as well as 60 and 300 for this factor, it could also equal 0 degrees or 180 degrees, okay? So the thing to be careful with, if you notice at the top of page 394 in bold type, it says, if an attempt is made to reduce an equation by dividing both sides of the equation by a term containing the unknown, we divided, in that first case, we divided each side by the sine of x. It contains part of the unknown, x, okay, in the trigonomic function. When we do that, the result may be defective, and the solution will not provide all the solutions of the original equation. In fact, all of the solutions are 0, 180, 60, and 300. We have 4 solutions to this problem, okay? So if you're going to divide trigonomic functions, both sides, it cannot have the unknown as part of the argument, okay? Otherwise, we'll get a defective answer, okay? So it's better to bring that expression all over to the same side, all the trigonomic expressions on one side equal to 0, and then go ahead and factor them out, okay? And you'll avoid that trouble. So that's just something to be aware of. So 2 lessons I did in this one video. You have 2 days to do 2 separate homework sets on this problem set 60. So I hope that helps. If you have any questions, shoot a text message or an email. Okay, so long for now.